Welcome back to part 5 on polynomials and their graphs. To find zeros of a polynomial p is to find the x-intercepts. And we're specifically interested in the behavior at those x-intercepts. To do that, we solve for p of x equals 0. And to find the zeros of a polynomial, factor it if possible and use the zero factor theorem. Some of you may have forgotten what the zero factor theorem means. What that's saying is take your binomial factors, let's say it's x minus c, and each one of those, we'll call this one x minus d, etc., and we set all of those equal to 0. Then each one of those binomials we set equal to 0 separately, and then we solve for x. So the polynomial real zeros can be stated in different ways, and I think that's why these are not always super intuitive the first time you see them, is because there's so many different ways you can say the same thing and mean the same thing. So if a polynomial p has a real number or root c, then the following are equivalent. 1, c is a 0 of p, meaning it's an x-intercept. 2, x equals c is a solution of the equation, and I actually just showed you that right up here, how you can find a solution to p of x equals 0 by setting the binomial equal to 0 and solving for x. 3, x minus c is a factor of p. So many different ways of saying the same thing. And 4, c is an x-intercept of the graph of p. So these are saying the same thing in 4 different ways. Now let's look at some specific behavior at the roots. So I'm going to compare multiplicities, and I know that might be a new word for you, but if we have a polynomial where one of the factors, x minus c, is of the form raised to a multiplicity, so raised to an exponent. Let's assume that m is odd and that m is greater than 1. Then the root of this polynomial will be at c. And the behavior at the root will be of the form of a cube, where it comes up, at the root it flattens, and then it crosses over. It could also have a different curve to it. It could possibly, now mind you, this is based on the total number of roots you have in your polynomial, but it could also cross from top to bottom of the x-axis. So it's more about the fact that it flattens out at the root and it crosses from one side of the x-axis to the other. Now let's look at the other possibility for your multiplicities. Let's say you have a binomial x minus c and it's raised to the m, and m, the multiplicity, is even. We also can say that m is greater than 1. In this particular instance, you still have a root at c, but your m has an exponent. Your multiplicity is either 2, 4, 6, 8, etc. It's even. And so when you have this situation, you will either have your root, you will just touch your root and then bounce back up. So you do not actually cross it. You can equal c as a root, but you cannot cross below into either negative territory or positive territory. You touch it and then you come back to where you were. So you could either have your root opening upward, so to speak, or opening downward. But for evens, you do not cross over. When your multiplicity is even, you do not cross over. You equal the root, and then you go back the way you came. So hopefully that makes sense. Okay, so note that the graph of a polynomial of degree n has at most n real roots. So that would mean that if we had a polynomial p of x is equal to 5x to the 7th plus 3x to the 5th minus 10x, that would have at most 7 real zeros. So we need to look at the two examples given and find the zeros of the following function. If I look at example 3a, where we have p of x equals 4x to the 3rd minus 12x to the 2nd minus x plus 3, we can factor this by grouping, I think. That will give us a 4 and an x squared as a common factor on the left side. If I factor 4x squared out, I will get x minus 3. Anytime there's a leading term that's negative in a factor by grouping problem, we factor that negative out, and I'll get another x minus 3. Ah, this is good. So now I can factor out of the whole thing x minus 3 as my common factor, and I'll be left with 4x squared minus 1. I'm setting this equal to 0 to find the zeros of the function. So I'm going to factor this x squared minus 1 further because it's a difference of squares. X minus 3 is one factor. 2x plus 1 and 2x minus 1 are my other factors, and I'll set that equal to 0. That means the zeros of this polynomial are x equals 3, x equals negative 1/2, and x equals 1/2. If I look at the degree or multiplicity of each one of these binomial factors, it's all of multiplicity 1, which means all of these roots will go straight through. They will not flatten out, they will not bounce, etc. So all you have to do is look at the end behavior first. The end behavior is odd degree and positive, which means it will start on the left and on the right. We'll have 3 roots wherever they end up being. So we'll just mark 3 roots. They'll go straight through and they'll look something like that. Now let's look at q of x. I have a common factor of x to the 3rd. Factoring out x to the 3rd will give me x squared minus 14x plus 49. If I factor that further, I will have an x cubed, an x minus 7, and an x minus 7. I am setting this equal to 0 because I want to find the zeros of the polynomial. Notice that the x minus 7 and x minus 7 are identical, so I can write that as a grouped binomial statement, and I will have x to the 3rd times x minus 7 to the 2nd. And it's important to notice my multiplicities. I have multiplicity 3 on the x and multiplicity 2 on the x minus 7. This means when I graph this, I will have end behavior that is odd positive. So it'll be on the bottom left and top right. So fill that in first before you do anything else. Now we need to find where the zeros of the polynomial are. X to the third is at 0. And x minus 7 is at 7. So we'll say it's right there. Now, since multiplicity 3 is at 0, it will behave like a cubic. It will flatten out and then go through. Since x minus 7 is to the second power, the multiplicity on x minus 7 is going to be the behavior of a quadratic. It will bounce at 7. Go ahead and give these a try.